Welcome back to the Deep Dive, where we take a single concept, run it through a stack of sources, and distill it down so you walk away truly informed.
And today we are following what is, I think, maybe the most persistent and uh, beautiful mathematical idea in human history.
We are talking about the number we call the golden ratio.
That's right. It's that constant, 1.6180339, on and on. It's often symbolized by the Greek letter phi.
And whether you look at pop science books, investment strategies, or, Renaissance art history, you've definitely been told that the single number is the secret key to all cosmic order, aesthetic perfection, and biological growth.
Oh, absolutely. The claims are huge.
I am ready to believe it, but our mission today is to test that claim.
Hmm.
We're going to trace the influence of phi from its rumored origin in ancient counting bones through the Pythagorean school's mysteries, all the way to its surprising reappearance in modern physics.
Precisely. Our deep dive today is to move beyond all those romantic claims and really unpack the historical record.
Okay, so where do we start?
We will examine the foundational mathematics that bind phi to its famous relative, the Fibonacci sequence. And then we'll critically determine whether the ratio's claims in art, architecture, and nature are, fact.
Or fiction?
Or maybe something even more interesting, a fascinating, undeniable mathematical inevitability.
Let's unpack this immediately, because the first thing our sources tell us is that the very name we use for this divine proportion, the golden ratio, it's a relatively recent invention. It's completely detached from the era that actually discovered its geometry. It's one of the most persistent misconceptions in mathematical history.
It really is. Given the reverence for this ratio since Euclid formalized it in the 3rd century BC, you'd assume the name golden section must be equally ancient.
Or at least from the Renaissance, when all the artists were supposedly using it.
That's what a lot of authoritative history books will tell you, even prominent ones. They often place its origin in the 15th or 16th centuries.
But that's just wrong.
That historical narrative is simply incorrect based on detailed source work. The common name golden section, or Goldinschnitt in German, has a formal origin date of 1835.
1835, that's truly modern. I mean, calculus was established, Newton was long gone.
Yeah.
That completely changes the perspective.
It does. The term was first formally published in a footnote by a German mathematician, Martin Ohm.
Ohm, as in related to the physicist.
Yes, the very same. His brother was Georg Simon Ohm of Ohm's law fame. In the second edition of his book, The Pure Elementary Mathematics, Ohm stated that this specific division of a line was, and I'm quoting here, customarily called the golden section.
Okay, so he didn't invent the phrase himself, but he documented that it was already in popular use, at least orally.
Exactly. He solidified it in academic German literature. And this documentation is crucial because it immediately shifts the context. The term gained traction in German literature throughout the 1830s, but its English debut appears significantly later.
When was that?
Not until 1875.
And where did it first pop up in English?
In an article focused on aesthetics, of all things, by James Sully in the Encyclopedia Britannica.
So not even in a math textbook.
No. Sully was discussing the experiments of a psychologist, Gustav Theodor Fechner, who was attempting to scientifically prove the ratio's alleged aesthetic superiority.
So the name, in English at least, was popularized not by geometry, but by this 19th century debate over what makes something beautiful.
That's the key. It immediately links the name to subjective taste rather than some immutable mathematical truth.
So before the 19th century, what did the giants of math actually call this ratio?
The terminology was way more intimidating. In Euclid's Elements, it was known as the extreme and mean ratio.
Right, which describes how you make it, but it's not very catchy.
Not at all. Later, during the Renaissance, the mathematician Luca Pacioli gave it a much more philosophical name, the divine proportion, in his influential 1509 book. But the everyday name, the golden section, is fundamentally a modern moniker. Now, to really appreciate the power of a number like phi, we have to go back way further than Euclid. We have to go to the very first steps humanity took in counting.
And this journey starts with a foundational question. Which came first, counting things, like 1, 2, 3, or ordering things, like first, second, third.
It seems intuitive to assume cardinal numbers, the how many developed first, for survival, how many berries, how many hunters.
That makes sense.
That was the initial assumption. But some anthropological research suggests ordinal numbers, the in what order, might have developed first, specifically in relation to rituals or ceremonies that required people to appear in a specific sequence.
So social order might have actually come before counting objects.
In certain linguistic contexts, maybe. But regardless of the order, the critical cognitive leap was realizing that, say, 2 hands and 2 knights are both manifestations of the abstract concept of two-ness, the number 2.
And that abstraction was messy.
Very messy. You can see the transition in early linguistics. In many cultures, the word for a quantity depended heavily on what was being counted.
Can you give us an example of that?
Sure. In the Fiji Islands, they had distinct words, koro for 10 coconuts, but bolo for 10 boats. They weren't using an abstract 10 that applied to everything.
Wow.
And in some New Guinea tribes, they had different words for a pair of males, a pair of females, or a mixed pair. The identity of the items defined the word for the quantity.
We even have remnants of that in English, don't we? A yoke of oxen or brace of pistols.
Exactly. And the earliest stage of counting appears to have been remarkably limited, focused purely on distinction. 1, 2, and then just many.
The famous 1, 2, many barrier. So 3 was still kind of a crowd in the earliest human math.
It really was. 5 millennia ago, in the Sumerian language, the word for 3, is, also served as the general mark of plurality. It was a conceptual boundary.
And this 2-counting system wasn't just in one place.
No, it was documented extensively in 19th century ethnographic studies. The Torres Strait Islanders, for example, they used Eurapun for 1, Okosa for 2, and then they'd combine them, like Okosa for 4.
Anything beyond that
was just Ras, which means many. The Bokudos and Aranda had similar, very restricted systems.
So that begs a pretty interesting question. Why did these systems consistently stop at 4 or 5?
Well, there are 2 major hypotheses. The simplest one links it to the 4 fingers on a hand, not counting the thumb.
Okay, that's straightforward enough.
But the more compelling explanation involves the physiological limit of human visual perception.
You mean the maximum number of items we can register at a glance without having to stop and count them one by one?
Exactly. Studies repeatedly suggest that limit is right around 4 or 5 objects. The human brain struggles to subitize, to instantly recognize a quantity beyond that point.
Like Kelly marks.
Perfect example. We draw 4 vertical lines and cross them with a 5th. That 5-bar gate system exists because it's hard to instantly distinguish more than 4 parallel lines.
So the limits of our early math might not have been cultural, but actually baked into our biology. And there's a fantastic anecdote that suggests this isn't even exclusively human.
Yes. Tobias Danzig's story about the clever crow.
Tell us.
A squire was determined to shoot a crow nesting in his watchtower, but the crow was clearly counting. If 1 man went into the tower and came out, the crow stayed away. If 2 men went in and 2 came out, it still stayed away. This worked up to 4 men.
So they were testing the crow's limits.
They were. The next day, they sent 5 men into the tower. 4 men then emerged and walked away. The crow, apparently unable to distinguish between a quantity of 4 and a quantity of 5, lost count, returned to its nest.
Oh, was shot.
And was shot. It's an old story, but it illustrates that this difficulty in grasping quantities larger than 4 or 5 might be a fundamental biological boundary.
So even before the mental leap to, say, the number 5, humans needed a way to record quantities. And our oldest records aren't scrolls, they're tally bones.
These bones show a need for systematic record-keeping long before written math. The oldest example, from about 35,000 BC, is a baboon's thigh bone found in Africa with 29 incisions on it.
But the real clue about abstract thinking comes from a wolf bone, right?
Yes, the 30,000-year-old wolf bone found in Czechoslovakia. It's remarkable because it has 55 incisions, but they're grouped specifically in sets of 5.
So it's not just a random tally. That grouping suggests an early organized concept of a base system.
It's certainly a precursor. It shows the use of a reference quantity, the hand, to manage larger counts, which is exactly what a base does. And this organizational need led to the 2 major base systems we see in history, base 10 and base 60.
Base 10 is the obvious one. We have 10 fingers. Aristotle even wondered why humans settled on 10 instead of a more mathematically elegant prime number.
And the answer is just pragmatic biology. Our bodies dictated our primary base. It's so deeply ingrained you can see it in language. The word 11, for example, comes from 1 left after 10. 12 is 2 left.
But then there's the massive outlier, base 60. The sexagesimal system seems completely arbitrary and incredibly complex for human memory.
Base 60 was the system of the Sumerians in the 4th millennium BC, and it's so stubborn it persists today in how we measure time: 60 seconds, 60 minutes in circles, 360 degrees.
How on earth did they manage it? A system needing unique names for 60 different numbers would be a nightmare to memorize.
They used a brilliant trick. They inserted 10 as an intermediate step to structure their counts, which cut down the memory load.
And why 60? Where did that come from?
The most accepted hypothesis is fascinating. It was likely a consequence of blending two different counting traditions.
From two different populations merging.
Exactly. Imagine one group using base 5 from the fingers on one hand, and another using base 12, maybe from counting the 12 joints of the four fingers using the thumb. 60 is the least common multiple of 5 and 12.
Wow.
Plus, 60 is divisible by 1, 2, 3, 4, 5, and 6, making it incredibly useful for fractions and trade. It was pragmatic, even if it seems complex to us.
It's amazing. The destiny of a number, whether it's a universal constant like phi or the base we count in, is tied up in something as simple as counting knuckles. Okay, let's fast forward to Europe in the 12th and 13th centuries. This is where Leonardo of Pisa or Fibonacci comes in. He bridges the gap between these ancient systems and modern arithmetic.
And he's famous for two crucial services to the West. One was completely intentional, highly technical, and it revolutionized commerce.
And the other was an accidental byproduct of a fictional rabbit population.
The intentional service was introducing the Hindu-Arabic place value system to Europe. He did this in his landmark 1202 book, Liber Abaci. Fibonacci had traveled all over the Mediterranean, absorbing mathematical knowledge.
He saw that the Roman system, with its I's and V's and X's, was just hopelessly clumsy for real business, especially compared to the Indian system, which crucially included zero.
He brought a new math to Europe's merchants, proving the Hindu-Arabic system was way superior for accounting and finance. This fundamentally accelerated trade.
But his accidental lasting legacy came from a really unassuming problem in that same book, the famous rabbit problem.
This problem was just an illustration of how to use the new numerals. The setup is simple, but in hindsight, incredibly powerful.
Right. A certain man put a pair of rabbits in a place surrounded on all sides by a wall.
How many pairs of rabbits can be produced from that pair in a year if it is supposed that every month each pair begets a new pair, which from the second month on becomes productive?
And the resulting sequence of pairs 1, 1, 2, 3, 5, 8, 13, 21, and so on is the Fibonacci sequence. The rule is simple. Add the last two numbers to get the next.
And the incredible power of this simple rule is that it governs growth and structures in places that have nothing to do with rabbits.
Like the family tree of a male bee.
A perfect biological example. A male drone hatches from an unfertilized egg, so it only has one parent. If you trace its ancestors, you get one parent, two grandparents, three great-grandparents, five great-great-grandparents. It's the sequence.
That's wild. It's a perfect demonstration of that recurrence relation in biology.
Even in physics. If you analyze the number of paths light can take reflecting between two parallel glass plates, the counts of emerging light beams also follow the sequence. 1, 2, 3, 5, 8. It's just everywhere. So while Fibonacci gave us the sequence from biology, the golden ratio itself emerged from pure geometry centuries earlier with the Pythagorean school in ancient Greece.
And their journey started not with growth, but with a pentagram, the five-pointed star. That was their sacred symbol of health and cosmic perfection.
That's the crucial link. The Pythagoreans discovered that the ratio of the diagonal to the side of a regular pentagon is exactly phi. But the structure of the nested pentagrams proves something that completely shook their entire worldview.
This is where we learn that phi is an irrational number.
Yeah.
You can't write it as a simple fraction, so its decimal just goes on forever without repeating.
Right. The pentagon's geometry provided a rigorous proof that its diagonal and side are incommensurable. They don't share any common unit of measure, no matter how tiny you make it.
And for the Pythagoreans, who believed the whole universe was ordered by whole number ratios, this must have been a catastrophe.
It was intellectual heresy. It undermined the philosophical foundation of their entire cult. According to the historian Iamblichus, the Pythagorean Hippasus was allegedly persecuted for revealing this truth.
Persecuted how?
Some legends say he was drowned at sea by his fellow Pythagoreans as a divine punishment for revealing the existence of the incommensurable.
So the golden ratio was literally a suppressed truth in ancient mathematics. But its link to perfection didn't stop there. Later, Plato connected phi to the structure of the cosmos itself, using the 5 Platonic solids.
That's right. Plato assigned 4 of the regular solids, the cube, tetrahedron, octahedron, and icosahedron, to the fundamental elements: earth, fire, air, and water.
And the 5th solid, the dodecahedron, which has 12 pentagonal faces.
Yeah.
It's constructed entirely using phi.
Exactly. And in his dialogue Timaeus, Plato assigned it to the universe as a whole, claiming the god used it for embroidering the constellations on the whole heaven.
So the geometry defined by phi was considered the ultimate cosmic blueprint.
This notion was incredibly influential. Aristotle later extrapolated this to postulate a mysterious fifth element, the ether or quintessence, a universal substance that made up the heavens. That idea of a light-propagating medium persisted for millennia.
Until the Michelson-Morley experiment proved it didn't exist, which ironically cleared the path for Einstein's relativity.
And now, modern cosmology has looped back and reused that very term, quintessence.
That's right.
Modern physicists, trying to understand the dark energy driving the universe's accelerated expansion, have dubbed one proposal for this force quintessence. It shows how these ancient ideas, rooted in phi, still echo at the frontiers of science.
Okay, so the Greeks gave us phi from geometry, Fibonacci gave us the sequence from biology. The monumental connection between these two seemingly separate ideas was made by the astronomer Johannes Kepler in the early 17th century.
Kepler was profoundly steeped in that mystical Pythagorean geometry. He was captivated by the pentagon and the divine proportion, and it's astonishing that he, centuries after Fibonacci, was the one to link the two.
How did he see the connection?
It's revealed in the purest definition of phi as a continued fraction. Imagine an infinite fraction. 1 plus 1 divided by 1 plus 1 divided by 1, and so on, forever.
So phi is defined by its own infinite recursive structure.
Exactly. Now, if you take successive approximations of this infinite fraction, if you stop it at different points, the ratios you get are precisely the ratios of consecutive Fibonacci numbers.
Right. You start with 2 over 1, then 3 over 2, which is 1.5, then 5 over 3, which is 1.666, then 8 over 5 is 1.6. They get closer and closer.
Kepler discovered this convergence around 1608. He noted that the ratio of successive terms in the Fibonacci series approaches the golden ratio. The ratio oscillates a little above, a little below, but its limit is phi.
And this link is so fundamental it seems to apply to all similar sequences. Tell us about that property where the starting numbers don't even matter.
This is a beautiful demonstration of what you might call mathematical gravity. Take any two arbitrary starting numbers, say 10 and 20. Now, apply the Fibonacci rule, add the previous two to get the next.
Okay, so 10, 20, 30, 50, 80, 130.
Keep going. By the time you reach the 20th term, the ratio of that 20th number to the 19th will be phi. It happens because all linear recurrence relations like this have a characteristic equation whose roots define the growth rate. For Fibonacci, the two roots are phi and its negative reciprocal little phi.
And phi is the dominant one.
Yes. Because phi is greater than 1, its powers grow rapidly, but the other root is about metas 0.618. Since it's less than 1 in magnitude, its powers shrink to 0 very quickly. No matter where you start, the influence of that smaller root just vanishes, and the sequence becomes utterly dominated by the growth factor of phi.
Which is encoded in something called Binet's formula.
A formula that lets you calculate the nth Fibonacci number directly using powers of phi. But it's wild.
It is. The Fibonacci numbers are whole numbers, right? You can't have half a rabbit. But the formula uses an irrational number, phi raised to a power, to calculate them.
Yeah.
How does that work?
That's where that other root, the conjugate, comes back in. The full formula is actually a combination of the two. It's basically phi to the power of n minus little phi to the power of n, all divided by the square root of 5.
Okay.
And because that little phi term shrinks so fast, it's just a tiny fraction. Subtracting it effectively cancels out the non-integer part of the phi term, leaving you with a perfect whole number. It's a beautiful demonstration of two irrational numbers interacting to produce a series of integers.
So the geometric purity of phi and the numerical perfection of the Fibonacci sequence would be just a mathematical curiosity if they didn't show up so consistently in nature, especially in things that need to grow efficiently.
And the most iconic example of this is the logarithmic spiral, sometimes called the growth spiral or spira mirabilis, the miraculous spiral.
What makes it so unique compared to other spirals?
It's the only spiral that maintains its exact shape as it grows. That's the definition of self-similarity. As you move outward, the angle between the curve and the radius from the center is always constant.
So it keeps its proportions while getting bigger, which sounds exactly like what a growing organism would need.
Precisely. You see this in structures built by accretion. The most famous example is the chambered nautilus shell. As the mollusk builds new, larger chambers, it retains the exact same cross-section shape, just scaled up.
And that specific shell shape was the direct inspiration for Frank Lloyd Wright's Guggenheim Museum.
It was a fantastic analogy. Visitors ascend a continuous spiral ramp, much as the nautilus moves through its chambers. The architect was mimicking nature's solution for efficient growth.
Where else do we see it?
In the growth of ram horns, elephant tusks, and even the flight path of a falcon when it's chasing prey. It tries to keep the target at a constant angular distance, creating a logarithmic spiral.
And it's crucial we don't confuse this with the spiral we see every day.
Yes, the Archimedean spiral. That's what you find in a roll of paper towels or a coiled rope. There, the distance between the coils stays constant. The shape changes as it gets larger.
Constant distance versus proportional distance.
That's the key difference. And tragically, this distinction was lost on the tombstone of Jacques Bernoulli, one of the spiral's greatest proponents. He was so fascinated by its self-similarity, seeing it as a metaphor for eternal life, that he wanted it engraved on his tomb.
With the motto, "Although changed, I rise again the same."
Exactly. But the mason botched the job and mistakenly carved the common Archimedean spiral instead. A sad irony.
And geometrically, the logarithmic spiral and file are inseparable.
Completely. You can trace it by connecting the vertices within a series of nested golden rectangles. If you start with a golden rectangle and cut off a square, the leftover rectangle is also a golden rectangle. You can do this forever, creating whirling squares. Connecting the corners generates the spiral. And if we move from shells to plant life, we find the Fibonacci sequence governing structures that demand efficient use of space and light. This is the study of phyotaxis,
which is Greek for leaf arrangement. It's about how leaves or seeds are arranged around a stem to get the most sun and rain and to minimize shadowing each other.
Exactly. The growth involves a screw-type displacement. If you trace the path from one leaf to the next, identical one above it, the number of turns and the number of leaves you pass often reveal ratios of successive Fibonacci numbers.
Give us some examples.
You can see a progression in nature. In basswoods, it's a 12:1 turn for every 2 leaves. In hazel and beech, it's 13 of a turn. Moving up the sequence, you find apple and apricot at 25. Pear and weeping willow are often at 38.
They're all successive Fibonacci ratios: 12, 13, 25, 38.
And the most stunning displays are where seeds or scales are packed really densely.
Like pineapples and sunflowers.
The superstars of phyllotaxis. A pineapple's scales are part of 3 distinct sets of spirals. Most pineapples will show 5, 8, and 13 spirals, or sometimes 8, 13, and 21.
And the sunflower seed head is breathtaking in its precision.
Sunflowers exhibit even higher Fibonacci numbers. You'll typically find 34 spirals going one way and 55 the other, or 55 and 89. In extremely large examples, pairs like 233 and 144 have been reported.
And it's not just seeds, right? Petal counts often follow the pattern.
Absolutely. Field daisies often have 13, 21, or 34 petals, all Fibonacci numbers, reflecting the spiral count in their genetic growth pattern.
So is this just a coincidence, or is there a deep mathematical reason why the golden ratio is so prevalent in this?
It is a mathematical inevitability for efficient packing. Growth algorithms show that you only get structures that look like real sunflowers when the growth angle used to place each new seed is precisely the golden angle.
And the golden angle is?
It's the angle that divides a full circle, 360 degrees, into 2 arcs whose ratio is phi. It's about 137.5 degrees. If a plant uses this angle, it ensures maximum dispersion.
Why does that angle work so well?
If the angle were a simple fraction, like 14 of a turn, the seeds would stack up in straight lines, creating huge gaps and shadowing. But because the golden angle is irrational, the placement of a new seed is never quite aligned with any previous one. This ensures each new seed is placed in the largest available gap. Evolution is basically funneled toward this one perfect mathematical solution.
Okay, we've established the golden ratio's geometric purity and its undeniable biological practicality. But now we get to its most controversial realm, art and architecture, where the core assumption is that phi is the key to aesthetic perfection.
And that assumption became widely popularized thanks to a pivotal moment in the Renaissance, where mathematics met theology.
That moment being the publication of Luca Pacioli's Divina Proportione in 1509.
Yes. This book was instrumental in moving phi from academic math into philosophy, religion, and art theory. Pacioli framed the ratio not just as a geometrical curiosity, but as a mirror reflecting divine concepts.
He listed 5 mystical reasons why phi deserved the name divine proportion. What were they?
They're magnificent examples of Renaissance thinking. First, he compared its unique single value to God's unity. Second, its definition requires 3 links, which he compared to the Holy Trinity. Third, he said its irrationality suggested its profound, unknowable nature, like God's omnipotence.
He was weaving geometry directly into dogma.
Absolutely. He even analyzed 13 effects of the ratio, stopping at 13, he said, for the sake of salvation, referencing the Last Supper.
Now, we have to mention the controversy. Pacioli is often accused of plagiarizing the work of another brilliant Renaissance figure.
That would be Piero della Francesca, the painter and mathematician. Pacioli is believed to have appropriated Piero's detailed analysis of the pentagon and the Platonic solids, all of which are tied to phi.
But regardless of the source, Divina Proportione was crucial because it came with stunning illustrations by Leonardo da Vinci.
Yes, drawn with his ineffable left hand. They were likely the first illustrations of skeletal solids, allowing artists to visualize these cosmic geometries and adding immense weight to Pacioli's claims.
But despite da Vinci's involvement, does it actually prove he consciously used phi in his own paintings, like the Mona Lisa?
Direct, unambiguous proof is surprisingly weak. The claims about the Mona Lisa are countless, with people trying to force golden rectangles over the frame, the face, whatever. But because phi is so close to a simple ratio like 1.6, it's easy to find approximate matches where none were intended.
What about the claim regarding St. Jerome in the wilderness?
Art historians trying to fit a golden rectangle around St. Jerome often need, quote, quite a bit of wishful thinking. The rectangle frequently misses critical parts of the body, or the arm extends way beyond its boundary.
So what's the strongest evidence we have from da Vinci?
It's actually a drawing, a head of an old man, where he used a grid for proportion. One rectangle in this grid is approximately golden. It shows his interest in mathematical proportion, but the lines are drawn so roughly you can't say it's definitive proof of conscious intent.
And if the claims about da Vinci are doubtful, the claims about artists who lived centuries before him must be pure speculation.
Absolutely. Claims that early Italian masters like Cimabue or Giotto used phi in their Madonna paintings 2 centuries before Pacioli are entirely unsupported by evidence. The measured ratios of these paintings are often closer to 1.5 or 1.6 than to the irrational phi.
What about the persistent myths around later masterpieces like the Parthenon or the pyramids?
Those were largely popularized by authors like Attila Gucca in the early 20th century, who blended sound math with inaccurate anecdotes. Detailed architectural analysis has repeatedly shown that neither the Parthenon nor the pyramids rely on the golden ratio. They use simple integer ratios, like 4:9 for the Parthenon, that are much easier to construct.
And modern masters like Georges Seurat, who supposedly attacked every canvas by the golden section.
Another misattribution. Detailed analysis of his compositions, like the Parade, confirms that while he was rigorous, his divisions are based on simple fractions, halves, thirds, quarters. The supposed golden ratio division just isn't there.
So who did use it consciously?
By the late 19th and early 20th centuries, as literature about phi surged, artists began adopting it intentionally. Paul Ceruzia explicitly stated he used phi to verify and occasionally to check his compositions.
And in more geometric schools of painting.
Definitely. The Italian painter Gino Severini consciously used it in the 1920s to achieve geometrical perfection. Later, abstract artists like Anthony Hill used a literal Fibonacci series of dimensions to define the parts of his sculptures.
So the whole premise that phi is the key to art hinges on the idea that the golden rectangle is the most aesthetically pleasing shape. And this was the claim of a German researcher, Adolf Zeising, in 1854.
Zeising hypothesized that phi governed all natural and aesthetic proportions. This led to the pioneering work of Gustav Fechner, the father of experimental aesthetics, who tried to verify this claim scientifically.
And his first attempt was a spectacular failure.
It was. He tried a public opinion poll at the Dresden Gallery about 2 Madonna paintings. Out of nearly 12,000 visitors, only 113 bothered to respond.
Later, more controlled experiments focused on the golden rectangle itself, but the results were inconsistent.
They were. Results varied wildly based on the orientation of the rectangle, its size, the cultural background of the participants, all sorts of things.
And the most famous negative conclusion came from a guy named Godkevich.
Yes, in 1974. He argued that any preference found was often just an artifact of the range of rectangles shown to people. If you only show extremely squat or extremely thin ones, people naturally pick the one in the middle, which happens to be near 1.6. He said there was little rationale left to regard it as a decisive factor in beauty.
But others still found moderate evidence for it.
Right. Chris McManus in 1980 found moderately good evidence for the phenomenon. But even he noted the critical ambiguity. It was impossible to tell if people preferred phi specifically or just similar, simple ratios like 1.6 or 1.75.
So the takeaway here is that aesthetic preference is subjective and can't be reduced to a single number. The idea of a fixed canon for ideal beauty is flawed, and the best artists are often the ones who break those rules anyway. Okay, the history of phi is full of these boundary jumps. The search for human aesthetic perfection led to controversy. Now let's see how the search for cosmic perfection, pursued by Kepler, followed a similar path of grand ambition and ultimate failure.
And the philosophical foundation here was the Pythagorean harmony of the spheres, the ancient idea that celestial motions produced consonant music based on simple whole number ratios.
Kepler was a true believer in this. He thought the universe was a reflection of the Creator and must be governed by perfect geometrical forms, specifically the 5 Platonic solids.
This led to his first monumental work, Mysterium Cosmographicum, in 1597. He wanted to answer 2 questions. Why were there exactly 6 known planets, and what determined the sizes of their orbits?
And his model used the 5 Platonic solids, including the phi-related dodecahedron, as a kind of cosmic nesting doll system.
He posited that the 5 solids were perfectly nested between the 6 planetary spheres. He placed the dodecahedron around Earth, the tetrahedron around Mars, the cube around Jupiter, and so on.
And how close was he?
Surprisingly close. The resulting distances agreed with observations at the time, often within 10%. It suggested his model was almost right.
So why do we call it a failure?
Because it was fundamentally wrong. The later discovery of Uranus and then Neptune completely destroyed the model. There was no 7th or 8th solid to accommodate them.
So why is this book still so important to the history of science?
Because it marked a crucial step toward the modern scientific method. Kepler took a metaphysical idea and created a concrete, falsifiable mathematical model based on empirical observation. He dared to quantify the universe and then check it against measurements. That process, even though he was wrong, was a cornerstone in the transition to modern physics.
And decades later, in his Harmonie Mundi, he actually developed tunes for the planets based on their orbital spacings.
He did. And having suffered immense personal hardship, he concluded that the Earth itself sang M-I-F-A-M-I for miseria, misery, and fames, famine, a bleak but mathematically expressed tune for our world.
Kepler was looking for perfect, smooth geometry. But modern science sees that nature is defined by highly irregular shapes, clouds, coastlines, lungs. This brings us to complexity and fractal geometry.
Coined by Benoit Mandelbrot, fractal geometry describes highly irregular shapes that exhibit self-similarity across scales. Just like the Nautilus, a small piece of a fractal looks statistically similar to the whole object, no matter how much you zoom in.
The classic illustration is the coast of Britain problem.
Mandelbrot famously asked, "How long is the coast of Britain?" The answer is that the measured length increases infinitely as your ruler gets smaller because the crinkles just persist at every scale.
Which means you can't measure them with standard Euclidean geometry. You need a new tool.
Exactly. You need the concept of a fractional dimension to measure the wrinkliness. The coastline of Britain has a fractal dimension of about 1.26.
So how does the golden ratio, the ratio of perfection, re-emerge in this broken, fragmented geometry?
It acts as a fundamental boundary condition. The Fibonacci-derived golden sequence is fundamentally self-similar. But more geometrically, when you try to build fractals by iteratively adding and reducing simple shapes, like squares, the structure only begins to fit together tightly to maximize density when the reduction factor is precisely 1/5 or 0.618.
So even in the math of irregularity, the ratio of perfection acts as a critical boundary for structural efficiency.
And this leads us to one of the most stunning, tangible examples of pure math predicting a real-world phenomenon, the discovery of the quasi-crystal.
This is a story of scientific dogma being shattered.
For decades, it was absolute dogma in material science that crystals, because they have to tile space in a repeating pattern, were strictly limited to 2-fold, 3-fold, 4-fold, or 6-fold symmetry. 5-fold symmetry was thought to be impossible.
Heresy, just like irrationality was for the Pythagoreans.
Then, in 1984, a scientist discovered an aluminum-manganese alloy that displayed long-range order and 5-fold symmetry. It was a complete shock.
But the structure of these new materials, called quasi-crystals, seemed to match a purely abstract mathematical exercise developed by Roger Penrose years earlier.
Penrose had created non-periodic tilings patterns that fill a plane without ever repeating, using only 2 specific shapes, a fat rhombus and a thin rhombus. These Penrose tilings exhibit fivefold symmetry, and the ratio of fat rhombi to thin rhombi approaches phi as the tiling gets bigger.
So the abstract math of Penrose tiling, defined by phi, suddenly described a physical structure in an aluminum alloy.
Precisely. And it got even more concrete when scientists used scanning tunneling microscopy. They found flat terraces ending in steps of two primary heights. The ratio of the high step height to the low step height was found to be exactly equal to the golden ratio.
That is a magnificent physical manifestation of an irrational number. It's truly mathematical anticipation of nature.
And finally, we turn to the contentious realm of financial markets where the Fibonacci sequence is used in trading strategies, assuming it dictates patterns in mass human psychology.
This is the Elliott wave principle, developed by Ralph Nelson Elliott in the 1930s.
Elliott observed that market fluctuations weren't random, but reflected human cycles of optimism and pessimism, adhering to a fundamental wave pattern based on Fibonacci numbers.
What's the core pattern he identified?
The basic pattern has 8 waves, 5 waves during an upward or motive trend, followed by 3 waves during a downward or corrective trend. And of course, 3, 5, and 8 are all Fibonacci numbers.
And like the patterns in nature, Elliott claimed this repeated fractally on shorter timescales.
Yes. A complete major market cycle, he said, could be broken down into lower-level waves corresponding to higher Fibonacci numbers, like 89 waves up and 55 down. The idea is that human sentiment aggregates in a way that respects this mathematical rhythm.
So how is this used today?
Modern trading algorithms use the golden ratio, 1.618, to calculate potential extreme points, or retracement levels. Traders assume that if a stock moves up, its correction will often be 61.8%, which is 1 over phi, of the prior move. Or if it extends, it might extend by 161.8%.
That seems like a bold leap, assuming that a number from geometry governs the irrational behavior of millions of global investors. What's the skepticism?
The main critique is that it's often used with massive flexibility. Analysts can always find a Fibonacci number to match past market moves by just redefining the start and end points of the waves. It's often accused of being a hindsight-driven system that can explain everything but predict nothing reliably. Still, its continued use shows that a significant number of market participants believe phi does indeed govern mass psychology.
We've seen the golden ratio influence everything from flower seeds to aluminum alloys and stock market volatility. The breadth of its application is why it remains so profoundly intriguing. We have completed a deep dive that spans the history of human consciousness, geometrical heresy, failed cosmological models, the elegance of the sunflower, and the chaos of the financial market. The golden ratio, phi, has a reach that is truly astonishing.
The mathematical power of phi and the Fibonacci sequence to appear in such distant phenomena forces us to confront a fundamental philosophical question. What exactly is mathematics?
The age-old debate. Is math invented by humans to describe the world? Or is it discovered because it's the fundamental language the universe speaks?
Our sources reflect the two powerful competing views. The modified Platonic view, championed by figures like Kepler and Galileo, argues that mathematical objects exist objectively, independent of humans. They believed math is the universe's language.
And the alternative, the human inventionist view.
Thinkers like Kant argued that math is a human invention, a system of axioms derived from how our perception handles lines and discrete objects. If a hypothetical liquid-based civilization existed, their math might be radically different.
But the consistent effectiveness of math in describing the physical world, how phi suddenly explains a quasi-crystal, makes the inventionist view hard to accept entirely.
This is where we propose the idea of complementarity, much like the historical debate about the nature of light. We eventually settled on the wave-particle duality. Light isn't purely a particle or purely a wave. It's a complicated phenomenon.
And mathematics is similar.
We invented the axioms, the rules, the game, based on how our human minds perceive the world, like counting on our fingers. But once those rules were established, we've been continuously forced to discover the objective, necessary properties, like the relationship between phi, Fibonacci, and the pecking of sunflowers.
So human logic dictates the terms of the game, but the universe dictates the inevitable results.
Which leaves us with a final provocative thought, relating all the way back to the origin of our counting. The power of mathematics relies on the consistency of human logic. But what if, as some modern theorists propose, our human logic itself was forced on us by the physical world through natural selection?
You mean our brains evolved specifically to recognize these patterns because they represented the most efficient structures for survival?
Exactly. then the universe may not be built on our invented language. Instead, our mathematics might just be the reflection of a numerical structure that was always there, waiting to be found.
A structure that began with tallying fingers and ended by describing the shape of the cosmos. That is a deep dive. Thank you for joining us. We will see you next time.